Radio Raurach Regionalnachrichten. Schweizer Halle. Die Agglomeration Basel hat am Samstag mit dem Grossbrand von einer Lagerhalle von der Sandoz in der Schweizer Halle ihren bisher grössten Chemieunfall erlebt.
That was the original news bulletin from Swiss Radio the morning after the accident at the Sandoz chemical factory. Sandoz was a pharmaceutical factory in Basel, Switzerland, who developed and manufactured medicine and pesticides. But on November 2nd, there was an accident. A fire broke out in the factory. Firefighters were called to the location and started to hose down the building. But in their attempt to put out the fire, they flushed a huge amount of chemicals into the Rhine. Somewhere between 10 to 15,000 cubic meters of contaminated water was released to the river. We've come to DTU in Lyngby, where we've met Stefan Trapp, a professor in impact assessment and water pollution at the Environmental Institute. How do you describe the immediate reaction from the public and from the government?
Well, I think the word panic is somehow correct. When the accident happened in Switzerland, there was no concern, you can say, so there were measurements of the air quality, all was okay. First there was given alarm, then it was taken back and everyone went to school and all, and then one day later came up these movies in the TV of all these dead fish and this red spill, this cloud of pollutants that went down the Rhine, and where it passed everything was dead. And then I think that was when the public and the politicians became aware that there is something. And this continued, and every day the cloud came further and new dead fish, and it was hundreds of thousands of fish, it was millions of fish that were dead, and it was seen as a big catastrophe, as a disaster. And everyone was of course shocked then, ecological catastrophe. Everyone was afraid that the Rhine, the big river Rhine in the heart of Europe would be dead forever. And well, that was the time of Chernobyl and the Waldsterben, and the public was very sensitive towards ecological issues anyhow, and in particular in panic of catastrophes. So I would say the main reaction was a kind of panic.
And what kinds of measures were taken to get an overview of this situation?
A day or two after the accident, the Rhine alarm was called by the Germans, but there was considerable confusion, you can say, at this time. First of all, because there was different countries involved, France, Germany, Switzerland, later also Belgium and the Netherlands. And there was no common body for reactions. So the immediate measures were little. It was more or less looking what happens, and yeah, I mean the movies in TV. But the drinking water supply was cut down for 3 weeks for all people that got water along the Rhine. Yeah, that was the main things I remember.
So let's try and see how contaminants' behavior in water is affected by different processes. We'll start out with advection, since it's the most important process. Advection considers the movement of particles in a fluid in the x direction. Advection can be described by this equation, where the concentration in a specific point of the river is estimated by the flow velocity. This makes it possible to follow the flow of the pollutants down the stream and estimate when it will reach the big cities. Another important process is diffusion, which considers microscopic random movement of molecules in all directions. The typical movement of particles is to move from higher to lower concentrations. This makes the pollutants completely mixed with the water after a certain time. This makes the spill of the pollutant spread to the entire width of the river. The molecular diffusion was first formulated by Fick and is known as Fick's first law, expressed by this equation. Notice the drop moves randomly and independent of each other. A third way of the pollutants to mix in the river is by dispersion. As diffusion was dependent on the molecular properties, dispersion is only a property of the flow processes. Dispersion is therefore caused by the turbulence in the water. Notice the drops move randomly in small parcels. Dispersion is mathematically described as molecular diffusion, but is often several orders of magnitude faster. In nature, diffusion, dispersion, and advection happen simultaneously. This equation shows the basic analytical solution for diffusion and dispersion advection, including a degradation term. In this equation, d is the sum of the diffusion and dispersion coefficients. U is the velocity and the term accounting for advection. And the last term is the degradation term. Notice that the first part of the equation is very similar to the probability density of a normal distribution. The similarity is explained by the fact that diffusion and also dispersion are independent stochastic movement of molecules. Thus the resulting density, that is the concentration, is normally distributed. Some initial and boundary conditions are necessary to solve the partial differential equations and to get this nice equation. Further details can be found in this book by Trapp and Matthews. The Rhine is the second largest river in Central and Western Europe with a length of 1,230 kilometers. The flow, width, and cross-sectional area changes significantly depending on the location. It was therefore split into 4 sections shown in red. These points were also measuring points after the incident. When the accident happened, a lot of different chemicals were spilled into the river. Yeah, and which contaminant was particularly worrying for the biodiversity?
Well, from what we know afterwards is that there were stored many insecticides. It was a storage hall from the chemical industry, from Sandoz, and there were 600 tons of insecticides stored. There was also a lot of other things stored, but the insecticides are of course chemicals designed to kill, and some tons of these insecticides were washed into the Rhine, and they killed all insects of course, and as they're nerve poisons they also killed all the fish, and this was probably the substance of most concern.
When the accident happened, a lot of different chemicals were spilled into the river. Most of the substances were insecticides, herbicides, and fungicides. The largest contributor was disulfiton, which is an insecticide, and this is what was chosen to model. For this model, the following assumptions were applied, and the flow velocity was found from historical data. On this graph, the elimination rate is plotted. The most important contributions are dilution and dispersion. Other terms include processes such as sorption, diffusion into sediment, hydrolysis, and so on. The other terms are included in the degradation term mentioned earlier. When looking at the results from the model, we see a very large peak a short distance downstream from the spill site. The concentration was measured to almost 600 micrograms per liter, and as the plume travels downstream, the maximum concentration decreases dramatically to 100 micrograms per liter in Plittersdorf, 180 kilometers downstream. At Koblenz, 440 kilometers downstream, the concentration drops to 31 micrograms per liter. When the plume reaches the Netherlands 7 days later and 700 kilometers from the spill, the maximum concentration reaches 24 micrograms per liter. All these values are well above the drinking water threshold of the time of 1.4 micrograms per liter, which meant that drinking water abstraction had to be shut down. What is important to notice is the width of the plume, which increases with time, increasing the time drinking water abstraction had to be shut down. A numerical model has also been made. In the numerical model, the total mass discharge to the river is divided into the first time steps covering the first 12 hours of the model. This means that the width of the plume is wider, and thus drinking water abstraction had to be shut down for a long period of time. Observe that the area under the curve of the numerical model does not change. This is because this numerical model does not consider degradation. Differentiating onto the curve will yield the total mass, which in turn is equal to the area. The numerical model has some advantages compared to the analytical model. That is, with a numerical model, it's easier to model spill that takes place over longer time periods or continuous leaching. Back at DTU, we asked Stefan Trapp to comment on the accuracy of these models.
Well, in principle, it's a possibility to predict it very accurately. I mean, the flow velocity is possible to predict with about 10% error. The dispersion is not so dramatic. The weak point is, as usual, the data. If there's an accident, there's normally not known how much chemical is spilled and how much is flowing down in the river. And thus it's impossible to make accurate predictions when not even this is known. Then what is also not necessarily known is the fate of the chemicals, the degradation processes, the sorption processes. Now we have databases for all chemicals in use in Europe and all chemicals that are traded, for example within REACH, but still someone has to access these databases and collect this knowledge, and then it depends of course on the temperature and the flow water level, the dilution. So it's because of the limiting data not possible to predict exactly the concentrations, which is maybe also not necessary. I mean, if the concentration is high enough, then there's concern, and then you only need to know when the spill comes and when it leaves, because while the spill is there, there's concern.